Alright, so we have already discussed all the asymptotic notations. Now let us take some practice questions. So the first question is that for any two functions fn and gn, fn is theta of gn if and only if gn is also theta of fn. The question essentially is that whether or not the theta relation is symmetric. Equal to relation is symmetric and theta is essentially equal to. So if we have to put an inequality against all of them, then big O is greater than or equal to, small o is strictly greater than, big omega is less than or equal to, small omega is strictly less than, and theta is equal to. And you know that equal to relation is symmetric, so that's why this statement is correct. Question number 2 is which of the following two statements is correct? The first statement is 2n square is big O of n square, and the second statement is 2n is big O of n square. Technically both of these statements are correct because 2n square is on the order of n square and 2n is on the order of n, and we know that on the order of n is also on the order of n square. But the first statement is a tighter bound, so this is a tight bound, whereas this is a very loose bound. A better statement would be that 2n square is big O of n square and 2n is small o of n square. So this is a much better statement, but technically both of these statements are correct. Next question, which of the notations is symmetric? So we know that there are 5 notations: big O, small o, big omega, small omega, and theta. Sometimes theta is also called big theta, but we are not getting into those technicalities. A symmetric relation is that if fn is related to gn, then gn should also be related to fn. Like plus operation in mathematics is a symmetric operation. Why? Because a plus b is also equal to b plus a. But minus operation is not symmetric because a minus b is not equal to b minus a. So in that sense, we can say that theta is symmetric because if f of n is theta of gn, this implies, so this will be if and only if gn is also theta of fn. For all others, we can't say that they are symmetric because greater than equal to is not symmetric, greater than is not symmetric, less than equal to is not symmetric, and less than is also not symmetric. So next question is about reflexivity. Reflexivity means that a function should be related to itself. Can we say that fn is big O of fn? Since big O has equal to also, so big O is less than or big O is greater than or equal to. So because there is equal to, so we can say that fn is equal to fn. So therefore fn is also big O of fn. Similarly, the omega relationship, the big omega relationship is also reflexive, and we know that theta is reflexive. But little o and little omega, they are not reflexive. Next question is about the transitivity. So transitivity means that if A is related to B and B is related to C, then A should be related to C. Like equality in mathematics. So if A is equal to B and B is equal to C, then by transitivity, A is equal to C also. Can we say that if Fn is big O of Gn and Gn is big O of Hn, this implies that Fn is also big O of, because if Gn is an upper bound to Fn and Hn is an upper bound to Gn, then by transitivity Hn is an upper bound to Fn. Similarly, omega relation, small omega relation, little o relation, and theta relation, they are all transitive relations. So all the 5 notations are transitive by nature. So next question is maximum of Fn comma Gn is equal to big O of Fn plus Gn. So this is also correct because Fn plus Gn will provide an upper bound to the maximum value of Fn or Gn. Here an unsaid thing is that all the functions that we are talking about, they are all positive functions. I have told in the video also that we are dealing with only the first quadrant of the Cartesian plane. It means that the number of arguments or the size of the input passed to the function is also positive and the function value is also positive. So if both f and g are positive functions, then f plus g will be higher than the maximum of f and g. That's why f plus g will provide an upper bound to maximum of f and g. And you will see that this is how we find the time complexity of merging logic. Even in graph. So let's say you have a graph and the graph is A, B, C. Let's say you have D also, then we have E also. So this graph has 1, 2, 3, 4 and 5. So there are 5 vertices. There are 5 vertices in the graph. If a graph has n vertices, then the maximum number of edges in the graph can be order of n square. And obviously the minimum number of edges can be 0. So the minimum number of edges in a graph is order of 1 and the maximum number of edges in a graph can be order of n square. Now both the traversals of the graph, whether it is DFS or BFS, both the traversals traverse all the vertices and all the edges. If there are V vertices in a graph and E edges in a graph, then the number of edges can be from 0 to V square. Actually, it is not V square, exactly V square, it is order of V square, but I am just writing it V square. Because both DFS and BFS traverse all the vertices and all the edges. So the total time taken by the traversal is V plus E. If number of edges are 0, then V will dominate the time complexity and the time complexity will be V. But if number of edges are V square, then edges will dominate the time complexity and the time complexity will become E. So essentially what we want to say is that the time complexity of the traversal of a graph is maximum of V comma E. So how do we denote it? You have seen in the graph algorithms that the time complexity of BFS and DFS is mentioned as V plus E. So this is the practical example of where this equation is used. Let's move to the next question. For natural numbers x and y, where y is greater than x, so y is greater than x, n plus x whole raised to the power y is order of n raised to the power y. Because y is greater than x, so we can say that n plus x will be less than n plus y. It means that y will raise the number much higher when added to n as compared to x. So this equation is also true. Running time of a function is on the order of n square. Is this statement machine dependent? So this we have already discussed in the very first lesson in the previous section, that our aim of coming up with this asymptotic notation is to find a way or find a measurement of an algorithm which does not depend on the machine. So these asymptotic notations are all machine independent and they focus only on the growth of the function or the algorithm. Next question. Is 2 raised to the power n plus 1 big O of 2 raised to the power n? So in this case also the answer is correct, because 2 raised to the power n plus 1 is nothing but 2 into 2 raised to the power n. So which is 2 times 2 raised to the power n, and this is big O of 2 raised to the power n, because 2 is just a constant which can be ignored. Therefore this equation is correct. Next question. Is 2 raised to the power 2n big O of 2 raised to the power n? This is not correct. So this is false. Why this is false is because 2 raised to the power 2n is actually 2 raised to the power n into 2 raised to the power n. And these two numbers which are getting multiplied are both given in terms of n. So we cannot say that x square is big O of x. So this is not correct. So therefore this is also not correct. So this statement is false. Next question. The running time of an algorithm is theta of gn. If and only if its worst case running time is big O of gn and its best case running time is omega of gn. So this is also correct. If we say that fn is theta of gn, it essentially means that we are saying that fn and gn are equal. So big O of gn means it is greater than equal to gn, and small o and omega of gn means it is less than or equal to gn. So if I say that the statement x is greater than equal to 2 and x is less than equal to 2, if I say that both of these statements are correct, it essentially implies that x is equal to 2. If a function fn is big O of gn and if a function fn is omega of gn, then the function fn must be theta of gn, and the other way around also. So this statement is correct. Prove that the set small o of gn and little omega of gn is an empty set. So small o of gn is strictly greater than fn and small omega of gn is strictly less than fn. So if this is fn, then the upper bound, which is strictly upper bound, and the lower bound, which is strictly lower bound, does not have anything in common. Therefore, their intersection has to be empty set. So this statement is also correct. Now let's also take some MCQs. MCQs is a good way to revise the concepts. So let's take some MCQs. Which data structure operations typically has constant time complexity? Accessing an element in an array by the index. So this has constant time complexity. This is correct. Next is searching in a binary search tree. So searching in a binary search tree, it will take log n time. So this is not constant. Sorting using merge sort takes n log n time. This is also not constant. And we have already seen that linear search takes order of n time. So this is also not constant. Answer is A. What is the time complexity of checking whether a number exists in a hash table? So when we discuss hash map data structure, we will see that all the operations in a hash map are constant time operations. So whether you are inserting the value in the hash map, or you are deleting a value from the hash map, or you are updating a value in the hash map, or you are just reading a value from the hash map, all of these operations on hash map takes constant time. So the answer is D. Next question, which of the following best describe big O notation? So tighter lower bound, tighter upper bound, average case bound, exact running time. We already know that this is a tighter upper bound. Next question, if an algorithm has the time complexity of big O of n cube, which of the following is also true? It is omega of n cube. This is definitely not true. I mean, it does not guarantee that it will be omega of n cube. It may be, it may be not. Next is, it is small o of n cube. This is definitely not true. Next is, it is theta of n cube. This is also not guaranteed. I mean, they may be true, they may not be true. So which of the following is also true? We cannot say for certainty, and the answer here is none of the above. Which notation describes the asymptotic tight bound of an algorithm? Asymptotic tight bound of an algorithm. So asymptotic tight bound is theta, because theta provides both upper bound and lower bound. So the tighter bound is only provided by theta, because big O and little o provides the upper bound, and omega and little omega provides the lower bound. Which notation is used to express an asymptotically strict upper bound? So if it is strictly greater than, it has to be little o. And next question, if fn is 5n log n plus 20n, what is the asymptotically tight notation? We know that to find the theta notation, we have to consider the largest power of n. So here the largest contribution of n will come from this part. Therefore, fn is theta of 5n log n. And because we do not consider the constants, so this becomes theta of n log n. So theta of n log n is the answer. Which of the following statement is true? N is little o of n log n. This is true because n is less than n log n. N log n is little o of n. This is not true. N square is little o of n. This is definitely not true because n square is greater than n. And log n is omega of n, little omega of n. This is also not true because n is greater than log n. So the only statement which is true is A. What does fn equals omega of gn signifies? We know that fn equals omega of gn signifies that gn is the lower bound of fn. So it means that fn will always be above gn, or the lowest point of fn can be equal to gn. Option B is correct because fn is asymptotically at least gn. It will be more than gn, but it should be at least gn. So fn is greater than equal to gn, which means that gn is less than equal to fn. So option number B is correct. If fn is theta of gn, which of the following must be true? Fn is big O of gn, fn is omega of gn, both A and B, neither A and B. So we know that if it is theta of gn, then it is also greater than equal to, and it is also less than equal to. Therefore, both of these statements are correct. So option C is the best option. Last question, for fn equals n square plus 1000n, which of the following is correct? Fn equals big O. So all of these notations are big O notations, and we know that big O considers the highest power of n in the function. So we can say that fn is big O of n square, and that option will be C. So option C is correct. I hope now the confidence in these asymptotic notations must have increased. From the next lesson, we will see how these notations are used in real life code. Thank you.